Welcome to the supplementary lecture in EE381. So this is an additional lecture that some students asked from me. So I would like to teach a little bit basics of the root locus method here in this lecture. This lecture is going to be different than the other lectures that I have uploaded so far. First of all, I'm going to be teaching only a summary here. I cannot teach all of the topics here because for root locus I generally spend 7 or 8 hours in a semester, and now I have only just 2 hours in this, maximum 2 hours in this lecture. So I won't be able to teach the root locus in very much detail. So I will only try to give the basics of the method and the meaning so that you can understand the uploaded notes by the other instructor. And the second thing is that I'm not as prepared to this lecture as I would be prepared to the actual lectures that I have taken so far. And so this is going to be more or less an improvisation, so please try to tolerate me. So here we would look at the concept of root locus. So when we look at the name root locus, the name tells us the following. So here the root means the closed loop poles in this context, okay? And the locus means trajectory. So the root locus method, what it does is that we try to show the closed loop pole trajectories as a single parameter of the system changes from 0 to infinity. So if I look at the closed loop system, I have the forward path transfer function given like this, and the feedback path transfer function, h of s, given like this. And we know that the closed loop transfer function is given by the feedback rule. G closed loop of s is g of s over 1 plus g of s h of s. Okay? And here we are going to be interested in the closed loop pole locations. We are going to be given g of s and h of s, and we are going to be wondering about what the closed loop poles are, or how they change when we change a single parameter k from 0 to infinity. So we are going to be looking at the following equation. We know that poles of this transfer function, closed loop transfer function, are determined by this equation. 1 plus g of s h of s equals to 0. So in general, this g of s h of s is going to have the following form: k over n of s over d of s. So g of s h of s is going to be dependent on a single unknown parameter, and this k is going to change from 0 to infinity. And then we are going to be looking at the roots of this equation. We are going to be looking at the closed loop poles as k changes from 0 to infinity. Since this gh is dependent on k, the closed loop characteristic polynomial is dependent on k, and that means that the closed loop poles are dependent on the parameter k. So as we change k from 0 to infinity, we would see that the closed loop poles will move in the complex plane, and we would like to draw their trajectories, and we would like to get some information about the closed loop system performance by looking at those trajectories. Okay? So here I will start with an example. So here I would have a closed loop system with a proportional controller, and the plant that I would like to control is 1 over s plus 2, and I close loop like this. So here our task is going to be to draw the root locus for this system. So here I have the open loop transfer function given as follows: k over, open loop transfer function is everything in the loop, k over s plus 2. So when I am given a transfer function, I can look at its zeros and its poles. So we see that this open loop transfer function doesn't have any zeros, no open loop zeros. And how many open loop poles do we have? In this case, just 2 open loop poles. And these are at s equals to 0 and s equals to minus 2. Okay? So, but we know that the performance of the overall system is determined by the closed loop poles. These are open loop poles and they are fixed. They do not change with respect to the parameter k. We know that the closed loop performance is determined by the closed loop transfer function or the closed loop poles. So, therefore, the first thing that I need to do here is to calculate the closed loop transfer function. G closed loop of S is going to be apply feedback rule k over s plus 2. This is a unity feedback system. That means that in the denominator I have 1 plus gh and h is 1 here. So we have k over s plus 2 here. So that gives us the following closed loop transfer function: s squared plus 2s plus k. Okay. So now, how many closed loop poles do we have for this system? We see here that the poles of the closed loop system are determined by this polynomial. So the characteristic polynomial is s squared plus 2s plus k is equal to 0. This is my characteristic equation. So we see that we have two closed loop poles. For any k value, we will have two closed loop poles, and we would like to change k from 0 to infinity, and then we would like to see how the closed loop poles would move. So when we start to draw a root locus, we draw the complex plane first. And then the first thing that we need to do is to mark the open loop zeros and the open loop poles. There are no open loop zeros there. That means that I have the following closed loop poles only: -2 and 0. Okay? These are the open loop poles and they are fixed. Instead, in root locus, we would like to draw the location of the closed loop poles. And in this case, because the characteristic equation is second order, the characteristic polynomial is second order, we can actually find the root locations or pole locations exactly. So if I write this equation as s plus 1 squared plus k minus 1 equals to 0, then this gives me s plus 1 squared is equal to 1 minus k. And if taking the square root of both sides would give me s12 is equal to -1 plus minus square root 1 minus k. Okay? These are my closed loop pole locations, and I would like to draw these root locations as k changes from 0 to infinity. Okay? And so how many branches do I, or how many trajectories do I need to draw here? Because there are two closed loop poles, there would be two branches. So two branches or two trajectories in the root locus. Okay? If I had three closed loop poles, then we need three trajectories, four poles, four trajectories, etc. Okay? So here I need to draw these locations as k changes between 0 to an infinity. Okay? So here what happens, the first thing that I want to draw is what happens when k is equal to 0. If k is equal to 0, this means that this is where the root locus starts, because root locus is drawn when k changes from 0 to infinity, so k equals to 0 means that it is the start of the root locus. Okay? Where are the roots? Where are the closed loop poles if k is equal to 0? If k is equal to 0, then the roots are at -1 plus -1. Okay? That means that if k is equal to 0, s1 is equal to, let us say, 0, and s2 is equal to -2. Okay? But these are nothing but the open loop pole locations, 0 and -2. Okay? So that means that root locus starts at the open loop poles. Okay? This is one of the rules that we're going to see. Root locus starts at open loop poles. So the closed loop pole locations are at the open loop pole locations if k is equal to 0. So the root locus starts here. These two trajectories, one of them is going to start here, the other one is going to start here. Okay? And then what is going to happen when I increase k? When I start increasing k, this number inside the square root is going to get smaller and smaller. That means that I am going to add -1. I am going to add and subtract to -1 a number which is smaller than 1. Okay? That means that these two roots are going to approach each other. Okay? If k is, for example, is equal to 0.1, these two roots would be here and here. If k is equal to 0.2, roots are going to come here and here. Okay? So therefore there is a movement of the roots towards each other here. And we are going to show this by actually shading this area like this. And I will put some arrows here denoting the motion of the direction of the motion of the closed loop poles. Okay? So here we have seen where the root locus starts and how they started. And we see that if I continue increasing k, these two roots are going to meet at a single point. If I increase k, until I increase k to the value 1, the roots are going to move towards each other and they will meet at a single point here. Okay? This point is going to be important for us later, and we're going to learn how to find such points, okay, where two roots, two closed loop poles would meet at a single point. Okay? And then this is the value k equals to 1. These values are k equals to 0, k is increasing, and k is equal to 1. Okay? If I continue increasing k above the value 1, what is going to happen? If k is strictly larger than 1, in that case I know that this number inside the square root will be complex. Okay? And that means that the roots are going to be -1 plus minus j k minus 1. Okay? If k is larger than 1, then I would have this type of roots. So if k is larger than 1, we are going to get complex poles, and their real part will always be equal to -1, and their imaginary part is going to be dependent on k. If k is equal to 0, we have two roots. K is equal to 1, we have two roots at -1. Here, this was the point k equals to 1. And if k is larger than 1, then we are going to have non-zero imaginary parts. That means that our roots are going to move here and here. And when I increase k, the imaginary parts would keep growing. Okay? So then we're going to show this type of motion by actually drawing here some other lines or branches with some arrows here. Okay? So this is going to continue until k goes to infinity. Okay? So this is a root locus for the closed loop poles. Okay? We see that for some k values, the closed loop poles are all real, and then at some point we have closed loop poles exactly at the same location, and after that k value, the root locations become complex, and we have complex conjugate poles whose imaginary parts would diverge to infinity. Okay? So then by looking at such a picture, we can really get lots of information about the closed loop system performance. Okay? So if I apply the route stability criterion to this polynomial, in that case, what would it give me? If you apply the route stability criterion to this polynomial, for which k values is the closed loop system stable? What would you obtain by looking at this picture? At k is equal to 0, there is a pole, closed loop pole on the imaginary axis, and if k is strictly larger than 0, then I see that all of the closed loop poles are in the open left half plane. That means that the stability range for the system, range of k for this system would be k larger than 0. K equals to 0 is not included because at K is equal to 0, we have one closed loop pole on the imaginary axis. So this makes the closed loop system unstable in that case. And I would have here these two poles moving here first, and then they're going to go into their complex domain, and they're going to go towards infinity like that. Okay, so this is the stability range that would be given to us by the route stability criterion for this system. And that is the only information that we can get from route stability criterion. But look at the root locus. We have really much more information given by the root locus about the system. For example, by looking at the root locus, I can predict oscillations in the step response of the system. If K is between 0 and 1, I see that both of the closed loop poles are real. So therefore, there won't be any oscillations in the step response of the closed loop system if K is between 0 and 1. On the other hand, if K is strictly larger than 1, we're going to start getting complex closed loop poles. That means that the closed loop system is going to get some oscillations. Its step response will have some oscillations if K is larger than 1. And what about the frequency of those oscillations? Frequency of those oscillations would be dependent on the imaginary part of the poles. And we see that the imaginary part gets larger and larger as K is increasing. And that means that I see that when I increase K, when the step response is oscillatory, then the frequency of oscillations of the response would increase as well. So here, this is what we see in terms of the oscillations in the closed loop step response. So what about the settling time of the system? So suppose that I ask from you to draw the settling time of this system by looking at the root locus with respect to the parameter K. What happens to the settling time of this system as K changes from 0 to infinity? Route stability criterion doesn't say anything about it, right? Because it just tells us whether the system is stable or not. But by looking at the root locus, I can try to understand what happens to the settling time of the system as K changes between 0 and infinity. So this is my K, and what about the settling time? We know that the settling time of a closed loop system is determined by the closest pole to the imaginary axis. Okay, so the closest closed loop pole to the imaginary axis. And if between K is equals to 0 and 1, the closest pole to the imaginary axis is this pole on the right. Okay, and we see that the closest pole is getting further away from the imaginary axis here as K increases. And what about the settling time if K is equal to 0? If K is equal to 0, we have a closed loop pole exactly on the imaginary axis. Okay? That means that the closed loop system is unstable if K is equal to 0, meaning that we have infinite settling time if K is equal to 0. What happens if K is between 0 and 1? So I have this 1 here. Between K is equal to 0 and 1, the closest pole to the imaginary axis gets further away from the imaginary axis. That means that the settling time decreases. Okay? If I increase K to the value 1, between 0 and 1, the settling time of the system would be decreasing. What happens when I increase K above the value 1? In that case, I have complex poles, and we see that distance of these complex poles to the imaginary axis would remain constant. That means that the settling time of this system would remain constant if K is larger than 1. Okay? So you see that we can actually try to draw the settling time, rise time of the system, or maximum overshoot of the system by looking at such root locus. So we see that this is really useful, and it gives us much more information than what the route stability criterion would give us. Okay? So of course this was a second order system, and we could find the poles, the closed loop poles, analytically. In general, we won't have that type of ability. So we would have a third order, fourth order, fifth order systems, and in general there wouldn't be any analytical expression for the closed loop poles like this. So in general, we would still like to draw such a picture, and we would like to interpret the transient performance characteristics of the system as k changes between 0 and infinity. So we would like to draw similar things for higher order systems, and that is what the concept of root locus is about. Okay? So here, before we start with the general topic here, I would like to first mention about the polar representation of complex numbers, which is going to be useful for us. Okay? So, polar representation of complex numbers. So here, what do we mean by polar representation? We mean the following. So I would have here a complex number in the complex plane, real of s, imaginary of s. This is the real part, and this is the imaginary part here. Okay? So this is my complex number here. And I'm going to draw an arrow here, and this complex number is nothing but a plus bj. Okay? This is my complex number. In general, we can actually represent the same complex number in polar domain. So this distance, what is this distance from the point 0 to the tip of this arrow here? We know that this is the magnitude of this complex number, and that value is nothing but a squared plus b squared square root. Okay? This is the magnitude of the complex number. And we know that there is an angle here, angle theta. And what is this theta here? And it would be just arctangent b over a. Okay? This is called the polar representation of a complex number with its magnitude and with its angle. Okay? So here, any complex number can be shown by its magnitude r and with its angle from the positive real axis. Okay? So here the interesting thing is what happens when we try to multiply or divide complex numbers in their polar representation. So here, in this case, I have this a plus bj, and the radius or the magnitude is square root a squared plus b squared, and I would have the angle is arctangent here, b over a. Okay? So suppose that you are given the polar representation of a complex number, how would you calculate its normal representation like this? So in general, it can be written like this. S equals to r theta. This is nothing but r cosine theta plus j r sine theta. Okay? If you are given the complex or polar representation of a complex number, then if you would like to obtain its Cartesian representation, then you would multiply the magnitude with the cosine of the angle here plus j times r times sine of the angle. Okay? So these are the conversion formulas between the polar representation and the Cartesian representation. So here, what I'm going to do is to show you what happens when you multiply or divide complex numbers with their polar representation. Suppose that you have two complex numbers, a1 plus jb1, and suppose that you have s2 equals to a2 plus b2j, jb2. Okay? Suppose that the first complex number has the following polar representation. R1, which is a positive or zero number, and this is also equal to R2 theta 2. Okay? Suppose that I calculate R with this formula and theta with this formula for both of the numbers here. Okay? Then what about S1 times S2? This is the multiplication of these two numbers, two complex numbers, A2 plus JB2. Okay? In that case, that means that I'm multiplying. So you know how to multiply two complex numbers like this, of course. But what happens when you multiply these two numbers in the polar domain? R1 angle theta 1 times R2 angle theta 2. Okay? If you multiply two complex numbers in their polar representation, this means that you're going to multiply their magnitudes. R1, R2, and the angles are going to be summed, theta 1 plus theta 2. Okay? So the polar representation behaves very well under multiplication. So when you try to multiply two complex numbers in their polar representation, you just multiply their magnitudes, and the magnitude of the result would be the multiplication of the individual magnitudes, and the angle of the result is going to be the summation of the angles of the individual complex numbers. Okay? So let us try to look at these two complex numbers. So I have real S, imaginary S. Let us say this is 1 and this is J here. Let us say this is my first complex number. S1 is equal to 1 plus J. And let us say S2 is equal to S minus J. S2 is equal to 1 minus J. Sorry. So suppose that I would like to multiply these two numbers. Okay? So I would have S1 times S2 is equal to, I will just multiply these here. So I have 1 plus J times 1 minus J. Okay? What is going to be the result? The result is just going to be the magnitude square of this number, which is equal to 2. If you don't believe me, just multiply these two numbers. So now I'm going to do the same thing, but in polar domain. Okay? What is S1 in polar domain? What is the magnitude of this? 1 plus 1 square root 2. Square root, the magnitude of this thing is square root 2. What about the angle? What is this angle? This is my theta 1. Okay? That theta 1 has to be 45 degrees. Okay? So S1 is just this number. What about S2? Its magnitude is again square root 2. And what about its angle? We see that this angle is negative 45. So what happens when I multiply these two numbers? S1, S2 is equal to, multiply the magnitudes, which is going to give you 2, sum the angles, which is going to give you 0. Okay? So magnitude 2, 0, angle 0. Okay? What is this number? This is nothing but 2 times cosine 0 plus J 2 times sine 0. But we see here that sine 0 is 0, so this is 1 here, so this is just 2. So we see that when I sum these two, when I multiply these two numbers, I just get this. Okay? So this number, which is 2, 2 and 0. Which is 2 plus 0, 0j. Okay? That is the multiplication, and in that case I am summing the angles that I have in this case. Multiply the magnitudes and sum the angles. So here we see therefore that any real number, any positive real number, I can write it in polar form as follows. So 2 angle 0 means that I have the number 2 here. Okay, this is the multiplication. So any real number can be shown as 2 angle 0. Okay. So what about the division of these two complex numbers? So if you divide S1 by S2, then you would have this 1 plus, so let me say here, A1 plus JB1 divided by A2 plus JB2. Okay? So this division is is much more difficult than dividing the numbers in their polar representation. Okay, so this is going to be R theta 1 divided R1 theta 1 divided by R2 theta 2. Okay, so when you try to divide two complex numbers in their polar representation, you divide the magnitudes first. This is the magnitude of the division, and the angle of the division is going to be the subtraction, theta 1 minus theta 2. Okay? So then let us apply this theory to these two numbers here. So S1 over S2, in this example I have 1 plus j, 1 minus j. Okay? So here what I would like to do is to express this number as a single complex number. So what I'm going to do is I'm going to multiply both the numerator and the denominator with the complex conjugate of this denominator. So multiply the numerator and the denominator by the complex conjugate of the denominator. Okay? And this is going to give me, this is going to be 2, 1 over 2 I have, 1 plus j squared, and this is going to be, I would have 1 plus 2j plus j squared is minus 1. So this 1 and minus 1 is going to cancel each other, and I would have 2j over 2, which is just j. Okay? And what is j in polar representation? So I'm wondering the number, the arrow of j here. Okay? What is this in terms of its polar representation? Its magnitude is 1. And what is its angle? Its angle is just 90 degrees. Okay? So I would have just this. So now let us do this division using the polar representation of these numbers. Okay? So if I divide S1 by S2 in polar representation, S1 is square root 2, 45 degrees. And S2 is square root 2 minus 45 degrees. Divide the magnitudes, 1, subtract the angles, okay? So it is 90 degrees. 45 minus 45 is 90 degrees, okay? So we see that we get the same result, but it was much easier here, okay? So now, how are we going to use this fact? Here you have to be really careful when looking at polar representations. If you have this number, so suppose that you have a complex number like this, a plus bj here. I have here this as r and theta. Note that this polar representation is not really unique here. The Cartesian representation is quite unique, but the polar representation is not unique. Why is that? Because this is the same as r theta plus 360 degrees. Okay? Theta, this is my theta, this is r. Theta plus 360 degrees would be the same angle. Okay? Therefore, in the polar representation, I can actually write r theta plus 360 degrees. Similarly, I can write r theta minus 360 degrees. Okay? So that means that I can actually add one more 360 here, or I can subtract one more 360 here. That means that this polar representation would actually remain the same if I add integer multiples of 360 to this angle. Okay? So I have r, theta is nothing but r theta plus k times 360. And here k can be selected to be any integer. Okay? So these are always the same. So here, when I look at the complex plane here, I would see that if I would like to consider the real number 1, the real number 1 is nothing but magnitude 1, angle 0. Okay? But it is at the same time k plus 360. Okay? So the number 1 is nothing but magnitude 1 plus angle 0 plus k 360. What about j? The number j is here. J is magnitude 1, angle 90 degrees plus k 360 here. What about minus 1? Minus 1 is here. Okay? And you see that the arrow changes its direction now. And I have minus 1 here. And we see that the magnitude has to be positive or 0. So minus 1 is going to have the magnitude 1. But its angle is going to be 180 degrees. Plus here, k times 360 degrees. Okay? Minus 1 has just this polar representation. So its magnitude is 1, and its angle is 180 plus k times 360. All right? So this minus 1 result is going to be important for us. So here I have 180 degrees plus k times 360. So therefore I have minus 1 is equal to angle magnitude 1. I have 2k plus 1, 180 degrees. The interesting point here about minus 1 is that I can write the following. Instead of angle 180, I can actually write here minus 180, which is the same angle. 180 is this angle, and minus 180 is the same angle here. Okay? So now, instead of 180, I can here write minus 180 degrees plus or minus k 360 degrees. Okay? So I can write the same thing like this, but this gives me 1n minus 2k plus 1, 180 degrees. So you see that it really doesn't matter whether I put a plus or minus 1 here. Minus 1, therefore, has the following representation. Okay? 1 plus minus 2k plus 1, 180 degrees. Okay? This is the polar representation of the number minus 1. Okay? So now we are going to go into the polynomial domain, and we are going to try to find the roots of some very simple polynomials. And then we are going to use this knowledge in developing a theory for the root locus. So suppose that I ask you the following question. Find the roots of the following equation. S cubed is equal to 1. Find the roots of this equation. S cubed equals to 1. In this case, we know that this is a polynomial. S cubed minus 1 is equal to 0. So there needs to be 3 roots. Okay? I know that as soon as you look at that equation, you see one root there. What is that root? S1 is equal to 1 is the trivial root here. But where are the other roots? Such roots can always be found if we use actually the polar representation of the number on the right here. Okay? So here, s cube is equal to 1 means that I know that in polar representation I would have 1 is 0 plus k times 360 degrees. Okay? What about s cube? Let us write s equals to r and angle theta. Sorry, this is wrong. R and angle theta, then this is going to be s cube is going to be s times s times s. So r theta times r theta times r theta is going to be 1 and k 360 degrees. 0 plus k 360 degrees would be this. So when you multiply complex numbers in polar domain, you multiply the magnitudes r cube and you sum the angles is equal to 1 k 360 degrees. Okay? So you see that we get the solution in polar domain in this case. So what does this mean? R cube is equal to 1. Now in this case this has only one solution because r should be a positive number. So I need to, in this case r is equal to 1. And what about 3 theta? It should be k times 360 degrees. Okay? So then what is theta? Theta is k times, divide 360 degrees with 3, 120 degrees. And here k can be any integer. Okay? Let us take k equals to 0. So the roots of this equation, I can write the following formula. S is equal to, magnitude should be 1. This is this one. And I have the angle should be k 120 degrees. Okay? Such a number, whatever I substitute k here as an integer, that would be a root of this equation. A solution of this equation. Okay? Let us try. If k is equal to 0, the magnitude is 1 and the angle is 0. So I have this number. Magnitude is 1, angle is 0. So I have the first root. So k is equal to 0, then s is equal to 1, angle 0, which is 1. Okay? I find the trivial root here. Okay? What about the other roots? Then I can select another k value to find the other roots. Okay? Let us choose, for example, k equals to 1. If k is equal to 1, then s is equal to, I would have the magnitude 1 and the angle 120 degrees. And how does that number look in complex domain? The magnitude is 1 and the angle is 120 degrees. So that number is going to be somewhere here. Okay, maybe not, maybe here. Okay? So this angle is 120 degrees, and I would have this number. What about the real and the imaginary parts of that number? So I can write this as 1 cosine 120 degrees plus 1 sine 120 degrees. Cosine 120 would be minus 1. So I would have here just minus 1. Sorry, cosine 120 is 1 over 2 plus 1 times square root 3 over 2. Okay? So cosine 120 is minus 1 over 2. Here I have this number is minus 1 over 2. And I would have here minus 1 times minus 1 over 2 plus 1 times. And sine 120 is square root 3 over 2. Okay? So this, and I would have a j here. Okay? So this root is minus 1 over 2 plus j square root 3 over 2. Okay? So you see that the second root is complex. It has a non-zero imaginary part. What about the third root? In that case, I can choose just another k value here. Okay? Just choose another k value. For example, k equals to -1. In that case, s equals to 1, and I would have minus 120 degrees. So this is going to be 1 cosine minus 120 degrees plus j1 sine minus 120 degrees. Okay? And we know that this is going to be minus 1 over 2 again, and minus j square root 3 over 2. Okay? And this number is going to be somewhere here. So these are the three roots of this equation, s cubed equals to 1. And we see that we can find them easily by looking at the polar representation of this number 1. Okay? If I write the number 1 as magnitude 1, angle k times 360 degrees, then I can find the roots here, 2 complex and 1 real root here. And in that case, each root is obtained, has the magnitude 1, and its angles are multiples, integer multiples of 120 degrees. So I have chosen 3 different k values, and then there are still infinitely many more k values I can try. What is going to happen? So is this equation, is it having infinitely many roots? So what happens if I choose k equals to 2, for example? Is it going to give me another root? If I choose k equals to 2, in that case, this is going to be s equals to 1, 240 degrees. But 240 degrees is nothing but this third root. This is 120, and this is minus 120 here. And there is here 120 more, so 240 would be just this angle, okay? So this would be 240 degrees. So it would just give this third pole or third root again, okay? So if you choose k equals to 2, then you would exactly obtain this last root that we have obtained. So the selection of the other k values will not give you new roots, but those roots would be on top of these 3 unique ones. So when we look at this equation, we have 3 unique roots of that equation, and they are given by these complex numbers. Any other root would be exactly on top of these 3 roots. Okay? So here, the interesting thing is that between these roots were 120 degrees. So why is this? Because I'm adding and subtracting 360 degrees for obtaining each different root. And because here I have 3 theta here in this angle, between the roots I would have 360 divided by 3, 120 degrees. Okay? Now I'm just going to give you a slightly more difficult version of the same problem. Okay? Suppose that now instead of solving s cubed is equal to minus 1, if s cubed is equal to 1, suppose I would like to solve just s cubed equals to minus 1. So instead of this, I will just try to solve this. Minus 1, and this is going to be s cubed plus 1 equals to 0. Okay? So now you again know exactly one trivial root, and minus 1 is the first trivial root of this equation. What about the other 2? Again, we need to use the same idea here. So I know that minus 1 is equal to 1 plus minus 2k plus 1, 180 degrees. Okay? So here you see the following: s cubed is equal to 1 plus minus 2k plus 1, 180 degrees. And instead of this, I can write r cubed 3 theta is equal to 1 plus minus 2k plus 1, 180 degrees. Okay? And this gives me the equations r cubed is equal to 1. Now this r cannot be complex, it's a real number, and that means that this equation only has a single solution, and that is r equals to 1. And what about the angle equation? 3 theta is equal to plus minus 2k plus 1, 180 degrees. Okay? Divide both sides by 3 plus minus 2k plus 1, I would have just 60 degrees. Okay? So now where are the roots here? Let us look at the roots here. Okay? So here this can be any odd number, any odd integer here. So the three solutions to this equation would be theta is equal to just 60 degrees. Theta equals to add 120 degrees. Again, there are three roots, and these roots are going to be 120 degrees away from each other, because we are always adding and subtracting here k times 360. Okay, so this is going to be 180 degrees, and add one more 120, 300 degrees or minus 60 degrees. Okay, so these three roots are going to be in the following: magnitude 1, angle 60. So the first root is here, magnitude 1, angle 60. So the second root is going to be magnitude 1, angle 180. So magnitude 1, angle 180 is here. But this is nothing but minus 1, right? The second root is here. This is a trivial root of that equation. And then the third one is going to be minus 60 degrees. Okay? So I would have here this one, minus 60 degrees. So this is my third pole. So we see that here again, the same type of idea gives us the three roots. So I have the magnitude of all roots equal to 1, and I would have the other roots having the angles 60, 180, which is going to give me minus 1, and minus 60 degrees here. Okay? So here again, what is the angle between these roots? The angle between these roots would be obtained by dividing 360 with the number of roots, which is 3. So I have the angle between the roots would be 120, which is 360 divided by 3. And what about the angle of the first root here? It is 60 degrees. So if you just find a single root here, angle of a single root, then you can obtain the angles of the other roots by adding and subtracting 120 to these roots. Okay? So this is the general rule. When you have such an equation, you need to obtain only a single root, like this, for example, and then you can add and subtract 120 degrees to those roots and obtain the other roots. Okay? So this actually gives you an idea for finding the roots of any type of equation like this. For example, s to the 4 equals to 1. Where are the roots here? I know one trivial root, which is equal to 1. So this is my trivial root. What is going to be the angle between the roots here? The angle between the roots is going to be 360 divided by the number of roots, which is 4. So the angle between the roots would be 90 degrees. So just add to this one 90 degrees. So you obtain this one, j. This is another root. Or you obtain this one, minus 1, another root. And add 90 degrees and minus j is another root. Okay, so you just find this type of roots by looking at the angle between the roots here. Let us finally try to do this. S to the 4 is equal to minus 1. In this case, do you know any trivial root? In this case, you see that no real number would satisfy this equation. Okay? No real number would satisfy this equation, which means that all of the 4 roots would be complex. Let us find only a single root. Minus 1 is just equal to 1 and 180 degrees here. Okay? This is just a single representation, polar representation, and I can add here k plus 360 degrees. Okay? So here I can find the first root as S1 is equal to take the what is the number? Take the 4th root of this 1, which is going to be 1, and divide this 180 by 4. It is going to be 45. Okay? So this is one of my roots. Magnitude 1 and the angle 180 divided by 4. And I have here k times 90 degrees. Okay? So I see that the first root has the angle 45 degrees, and the other roots can be obtained by adding and subtracting 90 degrees to the first root. Okay? But that is going to be the following. I have the first root here, and the others can be obtained by adding and subtracting 90 degrees to the other roots here, to the first root. So you see that both 4 roots are actually complex here. Okay, so now this was an introductory theory of polar representation of complex numbers. And now we're actually going to use this theory in obtaining a root locus. Okay? So these were probably the most difficult parts. So here let us look at the general theory. So I would have here G of S, and I would have here H of S. And we know that in general G of S, H of S would be looking like this: K times N of S over D of S. This is the open loop transfer function. Okay? This is our open loop transfer function. And now this is going to have the following structure: S minus Z1, S minus Z2, going until S minus Zm. I have M open loop zeros and N open loop poles. S minus P1, S minus P2, going until S minus Pn. All right? So now we are interested in the closed loop poles. We have seen that the closed loop poles can be obtained by solving this equation. Okay? This is the denominator of the closed loop transfer function. All right? And we can obtain the closed loop poles by solving such an equation. But this equation is nothing but the following: G of S, H of S is equal to minus 1. Okay? It just looks like our equation S cubed equals to minus 1. Okay? So if I write everything in polar domain, then I would have G of S, H of S. This is the magnitude of G of S, H of S. And the angle of G of S, H of S is here. And minus 1 is 1 in magnitude, and the angle plus minus 2k plus 1, 180 degrees. Okay? So this tells us that for an S value, for a complex number, to satisfy this equation, magnitude of G of S, H of S has to be 1, and the angle of G of S, H of S has to be plus minus 2k plus 1, 180 degrees. In control theory, this is called the magnitude condition. And this is called the angle condition. Okay? And now we would like to solve this equation, and there is actually a theory, or there is an illustration that explains this magnitude and angle conditions with respect to the poles and zeros, but I will not be able to do it here due to lack of time. Instead, I will try to explain the ideas on a single example. But before that, let us try to write this equation again by using the expression of the open loop transfer function. I have 1 plus, instead of GH, I can substitute K over N of S, D of S, is equal to 0. So the closed loop poles are determined by this equation. Or I can equate the denominators and I can write D of S plus Kn of S equals to 0. And this is the characteristic equation of the closed loop system. This is the characteristic polynomial. So this is characteristic polynomial. And this equation is the characteristic equation of the closed loop system. Okay? So we need to solve this polynomial for its roots for each k value. K is going to change from 0 to infinity, and in that case this polynomial is going to change. And we are going to draw the location of the roots of this polynomial as k changes from 0 to infinity. So we are going to find the roots of this polynomial, or we are going to draw the locations of the roots of this polynomial as k changes from 0 to infinity. This is what we did here. In the earlier example, I have the open loop transfer function was the following: k over s plus 2. Okay? In that case, n of s was 1, and d of s was s plus 2, and then this expression gave us the characteristic polynomial. D of s, s plus 2, plus k times n of s, which is 1, is equal to 0. S squared plus 2s plus k is equal to 0. Okay? So it was that root locus that we obtained based on this equation. All right? So now let us start with an example. Our example is going to be looking like this. So I have again a proportional controller, and instead of the system I have s plus 1, s plus 2, s plus 3, and s plus 4, and I have a unity feedback system given like this. And the task here is sketch the root locus, of course for the closed loop poles, as k changes from 0 to infinity. Okay? So now let us try to look at the equations here. The first equation that I'm going to write is going to be this one. Okay? 1 plus k n of s over d of s is equal to 0. So here the important thing is that I have n of s is equal to s, and d of s is equal to s plus 1, s plus 2, s plus 3, and s plus 4. So this is my d of s. All right? So open loop transfer function is given as following: k s over, I have these poles. So how many open loop zeros do we have? Open loop zeros. I have one open loop zero at s equal to 0. Only one open loop zero. And I have 4 open loop poles. S1 is equal to -1, S2 is equal to -2, S3 is equal to -3, and S4 is equal to -4. So 4 open loop poles and 1 open loop 0. Okay? So here is what I'm going to do. I'm going to write these equations first. So I have 1 plus k n of s over d of s. These are determining the closed loop poles. 1 plus k n of s is s. Okay? This is equal to 0. What about the next equation? I will write this one. So in the definition of the problem, we have defined m open loop poles, m open loop zeros. So in this case, m is equal to 1. And the number of open loop poles was defined as n. And in this case, n is equal to 4. Okay? So we have these numbers in this case. All right? So now let me write the other equation. I will repeat that equation so that I have a closer one. S this is equal to 0. If I equate the denominators here, I would get the characteristic polynomial. Okay? These are equivalent equations. So now we would like to solve these equations for different k values. And k is going to change from 0 to infinity. And for each k, we are going to find the location of the roots of these equations. Okay? The first question that I ask, how many closed loop poles are there? In this case, before the root locus, the first question that I ask is how many closed loop poles are there? For that, I'm going to be looking at the characteristic polynomial here. This is my characteristic polynomial. What is the order of that characteristic polynomial? You see that this is a fourth order polynomial and I have a first order polynomial. When I sum them, I would obtain a fourth order polynomial. That means that the characteristic polynomial of the closed loop system is fourth order. So how many closed loop poles should I have for this system? That means that this is going to give us the number of branches or trajectories. This is going to be 4. This is my first rule. So in the root locus, I'm going to draw 4 closed loop poles. And let us try to understand where the root locus is going to start and where it's going to end. So I will first draw here the complex plane. And then I will mark the open loop poles and open loop zeros. There is one open loop zero at the origin. And the open loop poles are here, 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 and here. Okay? So now I'm going to look at the start and end points of the root locus. So start points. Start points of the root locus would be obtained when k is equal to 0. Okay? So we would like to satisfy these equations when k is equal to 0. I can do the same interpretation from here, but this one is going to be easier. When k is equal to 0, where are the roots of this equation? When k is equal to 0, you see that this term is going to disappear. Where are the roots? You see that the roots are going to be -1, -2, -3, and -4, which are the open loop poles. Okay? So that means that the root locus starts at the open loop poles. Okay? There would be 4 trajectories here in the root locus, and each one of them is going to start from one of the open loop poles here. Okay? That is the easy thing. So the start points of the root locus would be -1, -2, -3, and -4. There would be 4 branches, and these 4 branches are going to start at the open loop poles. Okay? Let us look at the end points. This means that when k is equal to infinity, where are the trajectories going to go? The end points of the root locus means the points where the trajectories go to as k goes to infinity. These are called the end points of the root locus. Okay? So now let me look at this equation. So I will look at this equation and I would write the following: k times s plus 1, s plus 2, s plus 3, s plus 4 is equal to -1. Okay? So I have this equation and I would like to know where the root locus ends if k is very, very large. Suppose that k is very, very large. Suppose that k goes to infinity. Then where would the roots of such a polynomial be? So if k is very, very large, then I would have an infinity here. Okay? I would have an infinity here. Okay? So and there would be some numbers here. There would be some numbers, and there is an infinity here. Infinity times some number s, which I would like to find, divided by some other number should be -1. Okay? Infinity times some other number. Let me write this like this: k times s over s plus 1, s plus 2, s plus 3, s plus 4 has to be equal to -1. Okay? I would like to find s here, and I would like to find s when k is very, very large. If k is infinity, what number I can multiply k with, and I would get -1 as the result? When k is infinity, with which number I can multiply k with and obtain -1? I know that if this number is non-zero, then when I multiply infinity with that non-zero number, the result would be infinity. Okay? If this number was non-zero, when I multiply the infinity with that non-zero number, the result would be just infinity. As a result, the only possibility I can multiply infinity with here and obtain -1 as the result is that this number should be equal to 0. Okay? This division should be equal to 0, because infinity times 0 is undetermined. Okay? It can be equal to anything depending on your limits here. So here, the only possibility that this ratio can be for the multiplication of infinity times that number being equal to -1 is that this number should be equal to 0. Okay? And for this, and when is this division equal to 0? This division is equal to 0 if s equals to 0. But s equals to 0, what does it mean? S equals to 0 is the open loop 0. Okay? This is open loop 0. Okay? And so here, what can I say? The root locus starts at the open loop poles. It starts at the open loop poles and it ends at the open loop zeros. Okay? So when k goes to infinity, I see that one possibility is s equals to 0. So there are 4 trajectories starting from these open loop poles, and there is one open loop 0. I know that the root locus at k equals to 0 is going to start from these 4 points, and it's going to end at the open loop 0 here. But you see that one of the trajectories can go to here. So there are 4 open loop poles, but there is only one open loop 0. So are all of those trajectories going to go to that single 0? The answer is actually no here. So we can see here that only one of the trajectories starting from one of these points is going to go to this open loop 0. Where are the other ones going to go? So there are not sufficient open loop zeros here for all of the trajectories to end. So where are the others going to go? In order to be able to understand that, you have to understand when is this ratio equal to 0. So you see here that if I let S go to infinity in this ratio, let S go to infinity, in that case what would you obtain? So I would have S to the power 4 in the denominator and S to the power 1 in the numerator. If I let S go to infinity, in that case, I would see that this ratio again goes to 0. Okay? I know that as k goes to infinity, for this equation to be satisfied, this ratio should be equal to 0. And one possibility that makes this ratio equal to 0 is that S equals to the open loop 0. Okay? What about the other possibilities? The other possibility can be the fact that S can go to infinity. And when S goes to infinity, I see that here this ratio again goes to 0. Okay? So one possibility is S going to 0, or the other possibility is S going to infinity. Okay? Let us go back to this example. In this example, there were 2 open loop poles, here and here, and there were no open loop zeros. In that example, there were 2 open loop poles and no open loop zeros. What does that mean? That means that the closed loop poles will not be able to converge to the open loop zeros because there are no open loop zeros there. But the closed loop poles, therefore, since they cannot converge to the open loop zeros, they are going to go to infinity. And this is what is happening. Those closed loop poles, as k goes to infinity, are going towards infinity. Okay? So they are diverging towards infinity in the complex plane. Infinity in the complex plane, diverging in any place, in any direction towards infinity. Okay? So I see that the root locus starts from the open loop poles and they end at infinity. Okay? So here, this tells us that in the 4 trajectories that are starting from the open loop poles here, only one of them is going to converge to the open loop 0, and the other ones are going to diverge towards infinity. Okay? So when I try to draw the trajectories here, I will see that one of the trajectories starting from one of these open loop poles will converge to this 0, and the other 3 are going to diverge to infinity. Because that is what is happening here. There is only one 0 at S equals to 0, and there are infinite zeros here. So this ratio actually has one finite 0, which is at S equals to 0, and it has 3 infinite zeros. When you let S go to infinity, this ratio still goes to 0, meaning that it has 3 zeros at infinity when S goes to infinity. So in the root locus for this example, I would see that 3 of the trajectories would diverge to infinity. So 3 closed loop poles would go to infinity, and I would see that one of the closed loop poles will converge to this open loop 0 here. Okay? Maybe I should erase this one as well. Okay, so we have here obtain where the root locus ends. So root locus ends either at open loop zeros or at infinity. Okay? Root locus ends either at the open loop zeros or at infinity. So the next thing that we are going to obtain is the root locus on the real axis. Root locus on the real axis. Okay? So here I would like to understand where the points on the root locus would be included in my trajectories. Okay? So here, in order to be able to understand that, I will use the following equation. K S over S plus 1, S plus 2, S plus 3, S plus 4 is equal to minus 1. Okay? So now I will check which points on the real axis would be included in my root locus. Remember the earlier root locus that we have drawn. We have drawn this thing. Okay? And we see that some points on the real axis are included in the root locus. Okay? These shaded lines would be representing those points. The roots are coming from here and then meeting at a single point and going towards infinity. So these points on the real axis are said to be included in the root locus. And then we are wondering which points on this real axis would be included in my new root locus here. Okay? So we would like to solve this equation for some real S values. S is in general a complex number, but suppose that we are checking only on the real axis here. So suppose that we are checking which real S values can satisfy this equation for a single K value. Okay? And K is changing between 0 to infinity. Okay? Which S values would satisfy such an equation for a single non-negative K value? Let us try to understand here. I will first look at this type of S here. Okay? Suppose that I take a test point here. This test point S is here. It is a positive S value. Suppose that can such an S value satisfy this equation here? Okay? Let me ask you. So K is between 0 and infinity, and suppose that I take an S value, and suppose that S is positive, real and positive, and such an S value, can such an S value satisfy this equation? So here, if S is real and positive, this is a positive number. If the S is real and positive, this is a positive number, positive number, positive number, positive number. So this ratio is all positive, okay? And K is positive, but the result should be minus 1. Okay? So does it make sense? So I see that by using no finite positive S value here, I will be able to satisfy this equation. Because all of these numbers for a positive S value would be positive. K is positive, but I want the result to be equal to minus 1. Okay? So no positive S value can satisfy this equation. Okay? So S is larger than 0 is not possible. What about this interval? Okay? Let me write this interval. S is between 0 and minus 1. Okay? Do you think any S value in this interval can satisfy that equation for a single K value? Single non-negative K value. So now let us try to look at such a value. So S is negative. In this case, this is smaller than 0. What about S plus 1? S plus 1 is going to be positive. S plus 2 is going to be positive. This is positive, and this is positive. Okay? K is positive. Okay? Or larger than or equal to 0. Okay? In that case, can I satisfy this equation for some non-negative K value? So this is negative. Okay, S is negative. So all of these are positive. So this ratio is a negative number when S is real, and in this interval, this ratio is a negative number. K is a non-negative number, and the result is -1. So the signs match here. You see, by choosing a good S value, K value here, by choosing a suitable K value here, I can satisfy this equation because the result is negative and this multiplication is also negative. The only thing is the scaling that is coming with K here. So if my S is in this interval, then by choosing a suitable K, I can satisfy this equation because this ratio is negative and K can be selected to make the result equal to -1. Okay? So this interval is included inside the root locus. So there are some K values for which there will be some roots in this interval. So this interval is going to be shaded. Okay? Just like in the earlier case where we shaded this interval here. Okay? So now look at the case when S is between -1 and -2. Okay? When S is in between this interval, then do you think I can satisfy this equation? Okay? So let us try to look at that. If S is real and in this interval, then this number is going to be negative. S plus 1 is going to be negative. S plus 2 is going to be positive, right? This is positive, positive, positive. Okay? So I have two negatives in this case. Two negatives that will make a positive number. So the ratio would be positive. K is non-negative, but the result should be -1. So you see that whatever K value, whatever non-negative K value I select here, I cannot satisfy this equation for any S value in this interval. So this interval is not included in the root locus. What about the next interval? -2, -3. -3, S, -2. Let me look at the signs of these numbers here. So if S is real and in this interval this is negative, and what about S plus 1? S plus 1 will be negative. S plus 2 will be negative as well. S plus 3 would be positive. And S plus 4 would be positive. Okay? So I have two positives and three negatives, which would make a negative ratio. Negative ratio, the only thing I would need is some non-negative scaling to satisfy this equation. So you see here that by choosing a suitable K, I can satisfy this equation by selecting a real S in this interval. So this interval is included in the root locus. Okay? So I will shade here in this interval as well. So if you continue in this manner, you would actually see the following. This next interval will not be included, but the one after that is going to be included. So this interval is going to be included. So here, if you continue in this manner, -4 S -3 will not be included, and S smaller than -4 would be included. Okay? So you're going to see that these parts of the real axis would be included in the root locus. What does it mean? It means that there would be K values, non-negative K values, for which there would be some roots, some closed loop poles exactly on that real axis for some K value. So for some K value, there would be roots in this part of the real axis. So these parts of the real axis would be included in the root locus. Okay? So here, there is a pattern here, right? So when you look at these real axis points, you see a pattern, okay? And you see that when you skip one of the intervals, you include the other one. When you skip one of the intervals, you get the other one, okay? Because there is actually a rule for the points on the real axis included in the root locus. And our rule is as follows. A point on the real axis is included in the root locus if the number of open loop poles and zeros to its right is odd. Okay? So this is our third rule. The first rule was the number of branches. The second rule was the start and the end points of the root locus. And this third rule is the points on the real axis. A point on the real axis is included in the root locus if the number of open loop poles and zeros to its right is odd. If you look at such a point, when you look at such a point, if you look at the right of that point, there are no open loop zeros or poles to the right. Okay? If you look at this point, when you look at its right, there are no open loop poles or zeros to its right. Okay? So the total number of open loop poles and zeros to the right of this point is 0, which is not an odd number. As a result, this part of the real axis is not included in the root locus. If you look at such a point here, the total number of open loop poles and zeros to the right is 1. There is an open loop 0 here. Okay? So the total number of open loop poles and zeros to the right is 1. As a result, this interval is included. So when you look at this interval, the total number of open loop poles and zeros to the right is 1 pole, 1 zero, 2. Okay? Which is even. As a result, this interval is not included. And when you look at here, the total number of open loop poles and zeros to the right is 2 poles and 1 zero. The total number is 3, which is odd. That means that this interval is included. Okay? So, and you continue so on here. All right? So for a point on the real axis to be on the root locus, to be included in the root locus, the total number of open loop poles and zeros to its right should be an odd number. Okay? And these are these intervals. So here, as soon as I have completed this, and look at the other example here. In the first example, I had 2 open loop poles and no open loop zeros. Okay? When you look at this point on the real axis, the total number of open loop poles and zeros to the right is 0. So this part of the real axis is not included. This part is included because the total number is 1. This part is not included because the total number is 2. Okay? So we see here that this part is included, this part of the real axis is included because of this rule here. And remember that I have put some arrows here in the last time after I put the points on the real axis. So here, after I completed the points on the real axis here, I can put some arrows here. And these, because the root locus starts from the open loop poles, I put arrows going away from the open loop poles, going away from the open loop pole, going away from the open loop pole, and going away from the open loop pole. And because the root locus goes towards the open loop zeros, I put arrows going towards the open loop zeros. There's only one open loop zero, and the arrow should be pointing towards it. Okay? And as soon as you draw such a picture, you can guess actually what is going to happen here. this trajectory starting at this open loop pole is actually directly going towards the open loop 0. Okay? So one of my trajectories is going to be looking like this. Okay? This is one of my trajectories. And there is another open loop pole here, and this real line is included, this part of the real line is included in the root locus until infinity. So I see that the trajectory starting from here is actually going to go towards infinity, to negative infinity there, okay, on that line. And you see that there are two poles, two closed loop poles starting at here, and they're approaching each other. So when you see closed loop poles approaching each other like this, you can guess that a similar thing to this is going to happen. When the roots approach each other, they're going to meet at a single point, and then they're going to go into complex domain, and they're going to diverge towards infinity. So you see that only one of the trajectories is going to be converging to the open loop pole here. Okay? And the other three, two of them are going to go to infinity like this, and one of them is going to go to infinity towards the left. Okay? So you see that here, because there is only one open loop 0, we are going to have only one of those trajectories converging to the open loop 0, and the other ones are going to be diverging towards infinity. And actually, the last thing that we are going to see is how those poles diverging towards infinity will diverge to infinity. Okay? So we are going to see that divergence towards infinity cannot be arbitrary. Okay? So this pole really cannot diverge towards the left. We are going to see that these two are going to approach each other, and we are going to see that they are going to diverge towards infinity in this on such lines here towards the right. Okay? So the behavior by which these poles diverge to infinity as k goes to infinity is determined by the concept of asymptotes. Okay? So now let us look at the concept of asymptotes. So here, the asymptotes. We call the lines on which the root locus diverges to infinity as the asymptotes. Okay? So how many asymptotes are there? So in this case, we are talking about what happens as k goes to infinity. So as k goes to infinity, we see that some of the roots are going to diverge towards infinity. Okay? Some of the roots are going to diverge towards infinity. How many closed loop poles would diverge to infinity? In this case, we have 4 closed loop poles, and one of them is going to converge towards the open loop 0. Okay? And the other 3 are going to diverge to infinity. Okay? So then, how many asymptotes should we have in this case? So it is just going to be 4 minus 1. Okay? Because there are 4 trajectories, and from these 4 trajectories, one of them is going to converge to the open loop 0. So the number of the closed loop trajectories which are going to diverge towards infinity would be 4 minus 1. Okay? So the number of asymptotes here is 4 minus 1, which is equal to 3. Okay? So then what is going to be the angle of these asymptotes? I will look at, so I will draw here some lines, okay? And on these lines, some of the trajectories will converge on these lines and they will diverge towards infinity on those lines. And now I'm going to look at their angle. And in order to be able to look at their angle, I will use this equation, okay? So it is k times s over s plus 1, s plus 2, s plus 3, and s plus 4 is equal to minus 1, okay? So here k is a real number, and real and non-negative number. Therefore, it's polar. So I can write this polar representation as k magnitude and 0 angle. But before that here, so when k is very large and s is very large, how can I approximate this quantity on the left of this equation? When k is very large, this is going to remain where it is. When s is very large, this is going to remain where it is. But what about s plus 1? If the magnitude of s is very large, this 1 is negligible here. In s plus 2, if s is very large, this 2 is negligible here, 3 is negligible, and 4 is negligible. So therefore here, when s goes to infinity, then this quantity on the left can be approximated as follows. S over all of these finite numbers, 1, 2, 3, 4, would be negligible. So I would have here s to the 4. Okay? This is going to be equal to minus 1. This is this ratio, s over s to the 4 is this ratio when s is very large. Okay? Now let me look at this equation. This is going to be k over s cubed is equal to minus 1. Okay? But now we're actually going to be obtaining the following. This is going to give me s cubed is equal to minus k. Okay? So you see that this is an equation that we know how to solve. K is very large, a very large positive number, and I want to know what s would look like. Okay? So in this case, instead of s, I would write r times the angle theta, okay? And I would put here r cubed and 3 theta, this is s cubed. That is equal to, k is the magnitude of this number, the magnitude k, and the angle is going to be the negative minus 1 angle, plus minus 2k plus 1, 180 degrees. Okay? So this is what minus k is. K is a positive number, and minus k is going to be, its magnitude will be k, and its angle would be the angle of minus 1 here. Okay, a negative real number angle here. And if s equals to r angle theta, s cubed is going to be r cubed 3 theta. And now I can actually solve for the magnitude and the angle. So here, that tells me that r cubed, the magnitude is going to be k, and the magnitude is going to be cubic root of k. And we know that k is going towards infinity, so the magnitude is going to go to infinity. But what about the angle? So I have 3 theta is equal to plus minus 2k plus 1, 180 degrees. Okay? So here 2k plus 1 can be any odd number. Okay? So suppose that 2k plus 1 is equal to 1, then 3 theta is equal to 180 degrees. Sorry. So that means that theta is equal to 60 degrees. So then, what are going to be the other angles? What is the angle between these angles? So I would see that I would add 2k plus 180. So I would add k times 360 here. So the angle between these theta values would be 360 divided by 3. Okay? So I would have here, the other one would be just theta is equal to, add 120 degrees here, it is going to be 180 degrees, and add 120 degrees here, I would add 300 degrees, or minus 60 degrees here. Okay? So in general, so I would have three asymptotes, and their angles would be determined by these angles: 60, 180, and minus 60. Okay? So in general, we use the following formulas for the asymptotes. The angle of the first asymptote, we use the following formula: 180 degrees divided by 3. 3 is the number of asymptotes. So if this was 4, then I would have 4 theta here. Then I would divide 180 by 4 to obtain the angle of the first asymptote. So the angle of the first asymptote is 60 degrees here. And what is the angle between the asymptotes? The angle between the asymptotes is going to be, so I add and subtract here k times 360. I need to divide it by 3. So the angle between the asymptotes would be 360 divided by 3, 120 degrees. Okay? So these are the angle of the asymptotes, then the angle between the asymptotes. Finally, we have an intersection point of the asymptotes. I'm not going to show the derivation of it, but I will just write the formula. So if I have here the intersection point of the asymptotes is called the centroid. It's a real number. This is centroid, and it is actually obtained by the summing the poles, pi, subtracting the sum of the zeros, divided by n minus m here. Okay? Here n is the number of open loop poles, and m is the number of open loop zeros. Okay? In general, so this is my centroid formula: summation of the open loop poles minus summation of the open loop zeros divided by n minus m. In general, when we have n open loop poles and m open loop zeros, the number of asymptotes is n minus m. Okay? So in our example, we had 4 open loop poles and 1 open loop zero. That is why the number of asymptotes turned out to be just 3. Okay? So the angle of the first asymptote is in general 180 divided by the number of asymptotes. And finally, the angle between the asymptotes would be 360 divided by n minus m. So we would have these formulas for the asymptotes. Now the only thing that I need to do is to calculate this centroid. This centroid is a real number, and if I calculate it for this example, I would do the following. Sum the poles. The open loop poles are at -1, -2, -3, and -4. Sum these. It is going to give me -10. -10 minus sum the open loop zeros. Open loop, there is only one open loop 0, and it is 0. So this is going to be 0, divided by the number of open loop poles minus the number of open loop zeros. This is 4 for this example, and this is 1 for this example, and this is 3. So this is minus 10 over 3. So the asymptotes would meet at the point minus 10 over 3. Okay? So the asymptotes are meeting somewhere here. This is my centroid, and the angle of the first asymptote is 60 degrees. This is my first asymptote. Angle between the asymptotes is 60 degrees, and the angle of the second asymptote is 180 degrees. It is going to be here, because the angle between the asymptotes is 120 degrees. And here, there is my second asymptote. And the third asymptote is going to be 120 degrees away from this, which is going to have the angle minus 60 degrees. Okay? So I would have minus 60 degrees here. So this completes the asymptotes here. And now I can complete my root locus here. Okay? So I see that this pole goes to this 0. There is nothing to do here. And I see that this closed loop pole diverges to infinity on the second asymptote. This red line is my second asymptote. And you see that this pole, this closed loop pole, has from the start converged to this asymptote, and it is going towards infinity on that asymptote. And what about these two poles? These closed loop poles, they approach each other for some k values, and at some specific k value, they reach each other. So at some specific k value, I would have two closed loop poles at the same location. But if I continue increasing the k value, I would see that these closed loop poles go into complex domain. Okay? And then they will go towards the asymptotes. They would be diverging towards infinity on those asymptotes. Okay? So we see that this actually completes my root locus. So for being able to draw a root locus, you need to know only these four rules that we have covered so far. If you know these 4 rules, then you will be able to draw a rough figure like this for any pole 0 configuration you can come up with. Okay? So the rest of the rules are actually details here that I will not consider. So when you look at the root locus, you need to understand what that root locus means. So in this case, we have 4 closed loop poles, and these 4 closed loop poles at k equals to 0 start at here. Let me try to illustrate this picture in a better way. So when you look at a root locus, you need to understand a figure or a picture like this. So you have these closed loop, open loop poles like this. Okay. So when I look at such a picture here, you need to interpret this figure like this. There are 4 closed loop poles, and at k equals to 0, these closed loop poles are here, 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 at the open loop poles. Okay? When I increase k, this pole moves here, because it's going towards left. And these 2 poles move here and here, and this one moves here to the right. Okay? And then when I increase k further, this pole comes here, this pole comes here and here, and this one would come here. So for each k value, I have 4 closed loop pole locations, all right? And as I increase the k value, those 4 closed loop pole values would change their locations, okay? So for example, at some specific k value, these 2 poles would come on top of each other, and there would be 2 closed loop poles here at a single location, and this closed loop pole would be somewhere here, and this closed loop pole would be somewhere here. So again, I have 4 closed loop pole locations for that k value. Okay? If I increase the k value further, you would see that these 2 poles now comes here. So 2 closed loop pole locations, and this one approached this even further, and this one went away even further. Okay? So then you see that these 2 poles are going to go towards there on the asymptotes, and this one is going to come almost on top of this 0, and this one is going to get larger and larger in magnitude, and it's going to diverge to minus infinity. Okay? Of course, there are some important points on this root locus. For example, if I ask you for which k values do you observe oscillations in the step response of this system? For which k values do you observe oscillations in the step response of the closed loop system here? So for observing oscillations, you need to have some complex poles of the closed loop system. And in this case, we see that after some k value, we observe some complex poles here in the root locus. That means that we will start observing oscillations in the step response of the closed loop system after 2 poles reach each other at this single point. That point is called a breakaway point. Breakaway point. A point on the root locus where 2 poles reach each other, becomes on top of each other, and then they separate into complex domain. That is called a breakaway point. And you need to find this breakaway point, and you need to find the k value at which those 2 poles come on top of each other. So you need to determine what the k value here is in order to be able to answer the question of oscillations. If k value is strictly larger than the k value at which these 2 poles reach each other, then you would observe the oscillations in the closed loop step response. And then I can ask you, for example, for which k values is the closed loop system stable? You need to be able to answer such a question by looking at the root locus here. So here the important thing is that we see here that these 2 poles going towards the asymptotes, at some point they are going to intersect the imaginary axis. Okay? And when these 2 poles intersect the imaginary axis, if I increase the k value to a larger value, I would see that these 2 poles are going to go to the right half plane, making the closed loop system unstable. Okay? Then finding these imaginary axis crossings would be really important for you in a root locus for determining the stability range of this system. If you determine these intersection points and the k value at which those intersections happen, then the stability range of the closed loop system would be between 0 and the k value at which this intersection happens here. Okay? So these are some important points on the root locus. So the breakaway, or sometimes we have break-in points, and the intersections with the imaginary axis. These are the details of the root locus, for which there is also some theory, which I will not be able to go into in this lecture. Instead, this lecture This lecture was really too long. Sorry, I'm going to continue just a little bit, and I will draw some example root locuses. I won't go into these details, breakaway breaking points, or the intersections with the imaginary axis, but I will just try to draw some example root locuses by using the 4 rules that I have obtained so far. What are those 4 rules? The first rule is the number of branches or the number of trajectories. The second rule is the start and the end point of the root locus. The third rule is the root locus on the real axis. And the fourth rule is the asymptotes. Okay? Using these 4 rules, you will be able to obtain a general picture of the root locus. Then there comes the details like breakaway points, breaking points, or the imaginary axis crossings. There is also some theory for obtaining those points, but since I'm only going to be mentioning about the main points of the root locus here, I won't go into those. So here, in the rest of the time, I can maybe continue 10 or 20 minutes more. I will just try to look at this earlier picture. Okay? Suppose that I have 2 open loop poles, and they are here and here, -2. Okay? In that case, how many trajectories do you expect? In this case, in the earlier case, we had 4 trajectories because we had 4 open loop poles. And now I have 2 open loop poles, and therefore I need to expect 2 trajectories in the root locus. That is my first rule. The second rule is the start point and the end point of the root locus. Start points are the open loop poles, and the end points are the open loop zeros or infinity. In this case, there is no open loop zero. As a result, here, all of the trajectories, both of the trajectories will end up at infinity. Okay? Remember this figure. I'm trying to replicate this figure by using the rules here. And now, look at the root locus on the real axis. Here, the total number of open loop poles and zeros to the right is 0, so this part is not included. For a point here, the total number of open loop poles and zeros to the right is 1, which means that which is odd, so this interval is included. And here, the total number of open loop poles and zeros to the right is 2, which is even, so this part is not included. As soon as you put the points on the real axis, you can put some arrows going away from the open loop poles and going towards the open loop zeros. In this case, we don't have any open loop poles, but we can, so we don't have any open loop zeros, so we only have open loop poles here. So I can put arrows going away from the open loop poles here. So I see that these 2 poles are going to approach each other, and they're going to meet at some point, and then they need to go to asymptotes. What about the asymptotes here? So the intersection points of the asymptotes is going to be summation of the open loop poles, 0 open loop pole, -2 is an open loop pole, sum these poles, I would have -2 minus summation of the open loop zeros, which are 0, and n minus m. I have 2 open loop poles minus 0 open loop zeros. Okay, so this is going to give me -1. So the intersection point of the asymptotes is the point -1. This point is always a real number. Okay? And then, what is the angle of the first asymptote? Angle of the first asymptote. It is 180 divided by the number of asymptotes. 180 divided by the number of asymptotes, which is 2 here. And as a result, I would have the angle of the first asymptote is 90 degrees. Okay? What is the angle between the asymptotes? Angle between the asymptotes is twice that number. Okay? So it is 360 divided by the number of asymptotes, which is 2, and that is 180 degrees. Okay? So I have calculated the intersection point of the asymptotes, and the angle of the first asymptote is 90 degrees. That means that my asymptote would be making 90 degrees here. And the angle in between the asymptotes is 180 degrees, which is 180 degrees away from the first asymptote. So the second asymptote would be this one. So then what is going to happen? This completes all 4 rules, and I see that these 2 poles are going to combine at some point, and they're going to go towards the asymptotes, and they will converge to the asymptotes and will go to infinity on the asymptotes like this. Okay? So here, why do I not draw something like this instead? So I can ask you the following question. Sorry. So why do I not draw anything like this? Suppose you have these 2, and you have calculated the asymptotes. Why can't I draw something like this? So can a root locus look like this? The answer is going to be no. There are 2 reasons here. The first reason is not very important. We know that these points on the root locus these points on the real axis should be included in the root locus. If I draw a root locus like this, then these points on the real axis will not be included in the root locus. Okay? There are no roots on this real axis for any k values here. So this type of root locus would violate the rule for the real axis points. Okay? But here there is a more important reason that a root locus cannot look like this. So here, when I look at this root locus, when I have a complex pole at some place in this root locus, there is always its complex conjugate, which is also another root. Okay? So here, in this course, we are always talking about polynomials with real coefficients. That means that if on the root locus we have a complex pole somewhere, so if root locus passes from some complex point at some k value, then the complex conjugate of the same point will also be inside the root locus at the same k value. Okay? So the root locus would always be symmetric with respect to the real axis, because we are always working with polynomials with real coefficients. So when you see a root locus plot like this, you need to immediately tell me that it is wrong, because it is not symmetric with respect to the real axis. For this complex point, I do not have anything yet at its complex conjugate for the same k value. So this thing is definitely wrong here. Okay? Okay, so now let us try to draw another one. I am about to run out of brain power, so if I make a mistake somewhere here, I hope I can correct it in a fast way. So let me try to put some open loop poles here, and let me say that there is an open loop 0 here. Okay? So now here I would have 2 open loop poles and 1 open loop 0. Okay? And now I would like to complete the root locus for these root locations. Let us say that this is, so the values really are not important. So how many branches do I have? In general, the rule for the branches is max of m and n. M is the number of zeros, number of open loop zeros, and N is the number of open loop poles. Okay? So here there are 2 open loop poles and there are 1 open loop zeros. As a result, there would be 2 branches here. Okay? 2 branches, and these are going to start at these locations. The root locus starts at the open loop poles and it ends at the open loop zeros or at infinity. Okay? So now I'm going to fill in the points on the real axis onto the root locus. These points will not be included because to the right there are 0 open loop poles or zeros. This interval would be included because to the right there is 1 open loop pole and 0. There is no 0. So the total number is 1 here, which is odd. So this interval would be included here. So then this interval would not be included because total number of open loop poles and zeros to the right is 2, which is even. So this interval is not included, but this one will be included. The total number of poles and zeros to the right is 3 for this interval, and that means that this interval is included. So as soon as you put on the points on the root, points on the real axis, you start putting some arrows. Okay, the arrows should point towards the open loop poles and away from the open loop. The arrows should point towards the open loop zeros and they should point away from the open loop poles. Okay? Away from the open loop poles and towards the open loop zeros. So as soon as you put these figures, you start to see something here. These 2 poles are going to start here, closed loop poles, and then they're going to approach each other and they're going to meet at a single point. And you know what really happens after that. After that, they're going to separate into complex domain. Okay? They're going to separate into complex domain, and then one of them should go to this 0, the other one should go to infinity. But how the other one should go to infinity is determined by the asymptotes. How many asymptotes do we have here? In this case, n is equal to 2, number of open loop poles, and m is equal to 1, number of open loop zeros. So in this case, I have 1 asymptote. So there is no 2 asymptotes, so angle between the asymptotes is meaningless in this case. So 1 asymptote, what is the angle of the first asymptote? 180 degrees. Okay? That means that there is an asymptote at 180 degrees here. Okay, so the asymptote is here. All right? Here the starting point is really not important because you know its angle. The starting point is not really important. It is not important I started here, here, or here. Okay? So there is only 1 asymptote and it's going to go on this line because its angle is 180 degrees. So now I also know the asymptotes here. So now these 2 roots are going to approach each other. They are going to come on top of each other and they are going to go into complex domain. Then one of them should go to this 0 and the other one should go to this asymptote. How can this be? I would put here. So can I draw it something like this? This one is going to go to this 0 and the other one is going to go to the asymptote. Do you think such a thing makes any sense? Obviously not. In that case, root locus would not really be symmetric. Okay? So for this root location, there is no complex conjugate root. Okay? So really I cannot draw anything like this. Then how should it be? Here is what it is going to look like. This one is going to go here, and they're going to meet again at some point here. Okay? They're going to come here. There is a breakaway point here, breakaway point, and then they're going to separate into complex domain, and then they're going to meet again. Okay? This is called the break-in point. Okay? And then what is going to happen? If I increase k even further, one of these roots meeting here will go towards the 0. The other one is going to go towards the asymptote, towards infinity. Okay? So then you would have a picture given like this. So what can you say about the stability of such a system, such a closed loop system? You see that for small k values, the system would be unstable because there would be closed loop poles in the open right-half plane. But if you increase k above some specific value at which this intersection happens, if you increase k above this value, both of the closed loop poles would be in the open left-half plane and the system would be stable. So if you find this intersection k value, then if k is strictly larger than that value, you would have a stable closed loop system. What about the settling time of this system? What can you say about the settling time? And when do we obtain the smallest settling time? So obviously the system should be stable for finite settling time. That means that the two roots should be to the left here for finite settling time. And you see that for some k values, the settling time is going to be very large because here this distance would be very, very small here. But if I increase k further, settling time is going to get smaller and smaller. Okay? So these two roots are going to meet at a single point. And then if I increase k further, one of the roots is going to start approaching the imaginary axis, and the other root is going to start going away from the imaginary axis. I know that the settling time is determined by the dominating pole, closest pole to the imaginary axis. So in order to be able to find the smallest settling time for such a system, I need to determine the place at which the closest pole to the imaginary axis is furthest away from the imaginary axis. Okay? So here, the closest poles, both of the poles are the closest poles in this case, and the settling time gets smaller and smaller, even smaller now, because the root poles are getting away from the imaginary axis. And then I see here that they meet at a single point, then the closest pole starts to get approach the imaginary axis. So the settling time will start getting larger after this intersection point here. Okay? So the smallest settling time of this system is obtained at this break-in point. Okay? So at this break-in point, the closest pole to the imaginary axis is furthest away from the imaginary axis. Okay? Okay, the final example now, and in that case I will just add some complex open loop poles. Sorry. So let me say that we have a scenario like this. Okay? So let us say that I have two closed loop poles here, and let us say that I have two more here and here. Okay? So let me say that this is at -1, this is at -3 and -4. Okay? And let us say that there are no open loop zeros. So in this case, n is equal to 4 and m is equal to 0. All right? Now, how many branches or how many trajectories? 4 trajectories. Because the maximum of this number these numbers is 4. Okay? And what about the root locus starting points? So there would be 4 trajectories starting at these open loop poles here. Okay? And since there are no open loop zeros, all of the roots, all of the poles are going to end at at infinity. All of the trajectories will end at infinity, will end at the asymptotes. Okay? So now root locus on the real axis. So I look at these points, and to the right there are no open loop poles or zeros. So this interval is not really included in the root locus. Okay? So what about such a point? So you see that there are some open loop poles on this line. To the right, how many open loop poles and zeros? So when you look at such a point, you count all of the open loop poles and zeros to the right. So I see that here, there are 2 open loop poles here, and there are no open loop zeros. But this number 2 is just an even number. That means that this interval is really is not included either. So you see that since the complex poles are always coming in pairs to us, these two complex open loop poles will not really change anything in terms of the real axis. When you look at the real axis, you can equivalently forget about these complex poles here. So there are no part of the real axis on this axis would be, no parts of the real axis on this part will be included in the root locus. If I look at here, to the right, I have 1, 2, 3 open loop poles and 0 open loop zeros. So I would have the total number is 3. That means that this interval is included. And I will see that when I look at this interval, there are 4 open loop poles and zeros to the right. That means that the total number is even, which means that this part is not really included. Okay? So as soon as you draw these parts related to the real axis, you put some arrows going away from the poles, open loop poles, going towards the zeros. Here we have only open loop poles, so I put only arrows going away from the zero, and away from the open loop poles. And from these two would also come some arrows, but since I don't know the direction, initially I cannot put any arrows here. Okay? How many asymptotes do we have in this case? So n minus m is 4, which means we have 4 asymptotes. So what about the angle of the first asymptote? 180 divided by 4, 45 degrees. Angle between the asymptotes is twice that. 360 divided by 4, it is going to be 90 degrees. So there are 4 asymptotes. The angle of the first one is 45 degrees. Angle between them is 90 degrees. And what about the intersection point of the asymptote? Sigma 0, the centroid, is summation of the poles. So when I sum these two complex conjugate poles, their imaginary parts will cancel. Okay? So I will only sum their real parts, which would be -2. And I have -3. And I have -4, minus, there are no open loop zeros, 0 over 4. Okay? So this is going to be -9 over 4. All right? So these asymptotes would meet somewhere around -2, -9 over 4 here. That is the intersection point of the asymptotes. And we would have 45 degrees. This is the first asymptote. The other one is going to be 90 degrees away. So this is 90 degrees, and the other one is going to be 90 degrees away here, and the other one would be 90 degrees away. So I would have 4 asymptotes looking like this. Now let us try to see what is going to happen. It is easier to know what is going to happen to these two. These two are going to approach each other for some k values, and at some k value we are going to have a breakaway point. And after that breakaway point, these poles are going to converge towards the asymptotes, and they will go towards the asymptotes like that. And what about these? These two would directly start converging towards the asymptotes like this. Okay? So, and they are going to come together like this. So sometimes students think that the trajectories really cannot intersect the asymptotes. They can intersect the asymptotes. So sometimes these routes can come here and then converge back to the asymptote like this. Okay? It is really possible. The asymptotes only determine the behavior as k goes to infinity, when we are really far away, when s is really large, and when k is really large. So really, we really do not know, with the tools that we have seen so far, whether these routes are going like this, or they're converging to the asymptotes like this. We won't know, but it is not really very critical here. So they can go like this towards the asymptote. They can intersect the asymptote like this. They can even intersect the asymptotes more than once. Okay? So as long as they converge to the asymptotes as k goes to infinity, your root locus is counted to be correct. Okay? So what can you say about the stability range of such a system? We see that these two poles here, these two trajectories, for all k values, they are in the open left half plane. But we see here that these two poles, they go into the open right half plane for some large k values. As a result, the stability of the system is determined, of the closed loop system, is determined by for which k value these two trajectories would intersect the imaginary axis here. Okay? If you find this k value, then you find the stability range. The stability range of the system would be between 0 and that specific k value. All right? And what can you say about the settling time of this system? Since this settling time is determined by the dominant poles of the system, the poles closest to the imaginary axis, and I see that since these two poles are approaching to the imaginary axis as we increase k, we can say that the settling time of the system is getting larger and larger as we increase k, and as soon as k reaches to the value at which these two roots intersect the imaginary axis, the settling time becomes infinity. Okay? Because this closed loop system becomes unstable then. All right? So this was like a crash course on root locus. I'm not sure if this is really useful, because I'm going really fast and I don't explain some things in detail. So I'm not really happy about the quality of this lecture, but this is all I can do now. So I thank you for tolerating me. Bye-bye.